Today we're going to be doing some Calculus 2 practice problems, focusing on integration by substitution. So first, we're going to do some practice identifying u to the substitution and du for an integral. So recall that u is always going to be the inside function of a composite function. That's the whole reason we're using substitution, is because we don't like to see this composite function where we have an inside function of x cubed plus 1 and the outside function of the square root. So the u is always going to be the inside function because that will allow us to get rid of the composite. And du is always going to be the derivative of u. So that's going to be 3x squared with respect to x, of course. Now, that just changed the integral completely, simplified it completely, because we have this part of du. Of course, we're missing the 3, but that's easy to take care of because we can multiply by a special version of 1, 3/3, right? That doesn't change the value of the integral. But we can use the constant multiple rule, which we're used to taking numbers out of the integral, but it accomplishes the same as bringing them in. So we're just going to be left with a 1/3 integral of 3x squared, and of course that's part of du. And we took care of the composite function with u. So now this integral turns into 1/3 the integral of the square root of u du. And that is all the question asked us to do, was choose a u and du. And now that integral is going to be easy for us to solve, and we'll practice some of those later. But now let's look at another harder example. So of course we brought in trig. Let's see, what are we going to make u and what are we going to make du? You could do trial and error to figure it out, but just look for the composite function. So see how this one is composite because it has a function of sine of x and that squared function. So remember, u is always the inside function of the composite. So we can see that this is really just sine x squared. So the inside function of that composite function is sine x. And of course the derivative of sine x is cosine x. And that pretty much took care of the entire integral because we have all of du and we took care of the inside part for u. So now this rewrites to the integral 1 over, or I guess 1 du over our u squared. And of course that is also an easy integral to solve using the power rule. So that's all you have to do to identify u and du when solving integrals. And then of course solving the integral is the easy part. So let's move on to some examples of actually solving the indefinite integral, and they want us to check with differentiation, right? So let's look at this example. We're going to find a u and we're going to find a du and then solve the integral. So what do you think would be a good example or a good choice for u? I think it would be this inside function of the composite. Let's see. I think that's a good idea for two reasons. One, it is the inside function of the composite function. And two, its derivative, or part of its derivative, is right outside. So I know that this is going to be a perfect choice. Now let's see. The derivative of x to the 4 plus 3 is 4x cubed dx with respect to x, right? And let's see. We have the x cubed dx part. We're just missing the 4, so let's do the same thing. Multiply it by a special version of 1. Bring the top one in. Let's see, that's going to leave us with a 1/4 out front and the 4x cubed dx that we want, which is part of du. Now, and we already have our u, so let's simplify this to the integral or 1/4 of the integral, of u squared du. So now this super complex integral was changed to this much easier integral. We can do this 1/4. Let's do the integral. How do we integrate u squared? Well, it's just a power rule. We're just going to add 1 to the exponent and multiply by the reciprocal of that new number. So it's going to be 1/3 u cubed. And we know we did it right because if you were to take the derivative of this, the 3 would come out front and cancel, which we'll do in a second. Of course, we're going to add our constant of integration. Now, a little bit more simplification. We're left with 1/12, and let's plug back in our function of u. X to the 4 plus 3 cubed plus c. Now, I think this is the answer. But let's check using differentiation, right? This is one of our tools of calculus. We can just take the derivative of this, d over dx, of 1/12 x to the 4 plus 3, of course, plus c. And we really want that to be equal to what we started with, x cubed, x to the 4 plus 3 squared. So let's see. When we take the derivative of this function, notice that you're going to need a chain rule. Any time you're differentiating and you need a chain rule, when you integrate, you're going to need a substitution. The chain rule is always going to be the same as the substitution, which you will see in a second. So let's see. How do we integrate this? Well, remember when you do the chain rule, differentiate this. When you do the chain rule, you do the outside function first, so it's going to become a 3/12 and subtract 1 from the exponent, and then multiply by the derivative of the inside, which is 4x cubed. Now, and of course the derivative of the constant is 0. Hopefully this is equal to x cubed, x to the 4 plus 3 squared, because then we know we integrated right. Well, let's see, this 4 and the 3 are going to make a 12, which will cancel with that 12. And yeah, looks good. We have an x cubed, x4 plus 3 squared, which is of course equal to x cubed, x to the 4th plus 3 squared. So we know we integrated correctly. Now let's look at this other example. Another trig one. Well, let's see. U is always going to be the inside function of the composite function, which is sine x. Of course, du is cosine x with respect to x. And we have exactly that. So we know we are ready to integrate. It's just going to be u cubed du. It's going to be 1/4 u to the 4 plus c. And then let's plug back in our function of u, which was sine x to the 4th power plus c. Now hopefully when we take the derivative of this, 1/4 sine to the 4th power of x, we are left with what we started with, sine cubed x and extra cosine. So let's see. When we take the derivative of this, we're going to get 1/4. That power of 4 is going to come out front. The sine power is going to get reduced by 1. And then the derivative of the inside is cosine x. So that's just the chain rule. Hopefully that's equal to sine cubed x cosine x. Because then we know we did it right. So the 4 and the 1/4 cancel, and yep, we did it right. So we know that our answer here is correct. Now, let's look at another example, which is finding the general solution of the differential equation. Now, you might think, what does this have to do with integrals? I don't see an integral anywhere on this page. Well, when we're finding the general solution of a differential equation, we are looking for a function y of x that would make the differential equation true, meaning if we take the derivative of this function, we should be left with this. Now, they gave us the derivative, and they're asking us to find this general solution. So we're just going to work backwards using integration. This is where the integration comes from, to find the answer. So now notice that dy over dx is just, we can use multiplication to get that dx to the other side, multiply by both sides, right? So it's going to cancel on the bottom here, and it's just dy is equal to 4x plus 4x over the square root of 16 minus x squared dx. Now this is where integration comes in, because if we want our answer to be y being some function of x, but we only have the derivative of y, so that is where the integration comes in. So now let's see, on the left side we are left with y and some constant 1, right? On the right side, let's see, how do you integrate 4x? Well, it's just a power rule, add 1 to the exponent, and divide by that new number. You're left with 2x squared. We know that's right because if you take the derivative of that, you would just get 4x. And let's see, this is going to be much harder to take the derivative of, and in fact we're going to have to use a substitution. Now u is always going to be the inside of the composite, and du is going to be the derivative of that minus negative 2x. So let's integrate these two separately. Well, we already integrated the first one, but we can distribute this dx to both and then integrate them separately. So it's going to be plus the integral of 4x over square root of 16 minus x squared dx. So we're going to use substitution to solve this part of the integral, which will allow us to solve for the entire function. So let's see, of course, if we integrated them separately, there would be some other constant from the first one. Now let's see, if u is equal to 16 minus x squared, that means du would be equal to negative 2x dx. We have a good part of that, but we don't quite have it, right? So let's use some algebra to rewrite it. 2x squared plus c2. And let's also take the 4 out of the integral. That's going to leave us with an x dx over the square root of, let's just put in u now. And notice that we have x dx, but we're just missing this negative 2. So let's just put it there and account for that with a negative 1/2 out front like we did in the other examples. So now we can rewrite this as 2x squared plus c2 plus, now what does 4 and negative 1/2 make? Well, that makes negative 2 integrals of du over the square root of u. So now just a little bit of ugly math. Y plus c1 is equal to 2x squared plus c2 minus 2 integrals. I'm going to rewrite this as u to the negative 1/2 du, and let's just do a power rule. So let's focus on the integral here, so we don't have to keep rewriting. How would we integrate this? Let's see, we're going to add 1 to the exponent, which would give us u to the positive 1/2, and we are going to multiply by the reciprocal of that, which is 2. So the integral turns to that, and our entire problem turns into y plus c1, and of course there is a third constant from the third integral. This is equal to 2x squared plus c2, and we have a negative 2 times our integral. So it becomes negative 4 u to the 1/2. Let's just plug back in our u function, which was 16 minus x squared. And of course we have minus 2 c3s. Now, you might be confused at all these c1, c2, and c3s because maybe your textbook just skips this and goes to show that all of them are just constants, which means that all of them are going to create a new constant. So, our final answer is 2x squared minus 4, 16 minus x squared, that's my power up here, plus that new constant c that is represented by the sum of c1, c2, and minus 2 times c3. We can just call that one big constant because the derivative of just the big constant or all of the little constants is the same, which is 0. So this would be the solution of our differential equation, meaning that if you took the derivative of this, you would be left with what we started with. So that was a bit ugly. Hopefully this one is not as ugly. Let's see. We're going to start the same way by multiplying both sides by dx. So dy is equal to x plus 1 over x squared plus 2x minus 3 squared dx. And let's integrate both. And this time I'm going to skip the constant 1 and constant 2 and just call at the very end the big constant like how we did last time. So I'm going to just say that y is equal to, let's see, how are we going to do this? We're going to need a substitution, obviously, but what should u be and what should du be? Well, let's see, I think u should be the inside function of the composite function. So we can see the composite function is here, and of course this is the inside function. So x squared plus 2x minus 3 would be u, and the derivative of that would be 2x plus 2 with respect to x. So we don't quite have that, but you can see we have half of it. So all we'd have to do is multiply it by 2, which means we only have half of the integral. Remember what we did earlier by taking the 2 and bringing it in? That's kind of what we did. So we are left with 1/2 of the integral. And notice that this and this make our du. And of course on the bottom we have u squared. So it would be du over u squared. And this is just an easy power rule. So y is 1/2. Really, this is u to the negative 2 du. So when we add 1 to the exponent, we're left with u to the negative 1. And when we multiply by the reciprocal of negative 1, which is just negative 1, we get that. And of course our c. So now all we have to do is plug back in our function of x squared plus 2x minus 3 for u. And let's see, we get, and I'm going to bring the negative out front, 1 over u, or x squared plus 2x minus 3 plus c. So this is our general solution to the differential equation. Now let's move on to another set of examples, this time being harder indefinite integrals. So this one's a complex trig one, and this is an exponential one. Let's see, how are we going to solve this? We're obviously going to need a substitution because we have a composite function. And we're going to need to find the du of that. So u is going to be the inside of the composite function, 1 over theta. And what I find is a lot of students will get confused when they see this theta because they haven't seen it since trig a while ago. But it's really the same as x or u. It's just a variable. And as long as your derivative is with respect to that variable, you could just think of it as x in your mind if that makes you feel better about it. But anyways, u is 1 over theta, which means du is negative 1 over theta squared with respect to theta, which you can do the math. And let's see, that's going to immediately make this integral cosine of u. And do we have du? Well, we have negative du, right? Like, there should be a negative in here. So we can account for that by just putting a negative up front. This negative doesn't change the value of the integral because it's still technically a positive. So, but of course, this negative and this function and this d theta all make our du. So for us to put this du right here means that we're still going to have that negative out front. That's going to make it negative integral. What's the integral of cosine u? Well, the derivative of sine is cosine, so the integral of cosine is sine. And all that's left is to plug in our function of u, and let me do it down here. Our function of u was 1 over theta, right? Plus c. So that was a bit of a harder example. And what about this one? So later in calculus 2, you'll figure out how to integrate with multiplying using a process called integration by parts, which can get ugly. But you could just skip that hard multiplication process by recognizing it as a substitution problem. You can see that u, or I see a composite function here, right, where x squared is the inside function, and the derivative of that is 2x. So you can see we have a good portion of that du. All we need is a 2. So we're going to account for that with a 1/2 out front. So now we have our du and we have our u. So this is just 1/2 times the integral of e to the u du. The best part about this integral, or this is the best integral, because the derivative of e to the u is e to the u, which means the integral of e to the u is e to the u. Super easy. Of course, the last step is to plug back in your function of u, and don't forget the constant. So fairly similar to what we started with. The 1/2 gets traded out for an x, which makes sense because when you take the chain rule of x squared, it brings a 2x out front. So the 2's cancel and you're left with an x. So now let's move on to our final 2 example sets. One is going to be this substitution, but a problem happens. Let's see, when we start to do the substitution, you're going to hopefully choose x plus 6 being your substitution because it's the inside of the composite. And du is super easy, it's just dx. So I forgot my dx. And you might get confused because notice that now our integral, square root of u du, but we have this x. This x messes us up, right? Because we're deriving with respect to u. So what we're going to do is simple, but it can get confusing. Notice that u equals x plus 6. So couldn't you do a little bit of algebra to just figure out what x is? Couldn't you subtract 6 from both sides to see that x is equal to u minus 6? So all we're going to do is change of variables to just get rid of that x. So x is equal to u minus 6 times the square root of u du. Now this just made the integral a bit more challenging because we're going to distribute that square root of u, leaving us with u times the square root of u, which is u to the 3/2, minus 6 square roots of u, which is u to the 1/2. du. So we can integrate them separately and find out that this first integral is going to turn to just a power rule, u to the 5/2 when you add 1 and then multiply by the reciprocal. We're going to subtract 6. When you add 1 to that, you get u to the 3/2 multiplied by the reciprocal. And that's it. Just add c. We're going to simplify a bit and plug back in our function of u, which was x plus 6. So 2/5 x plus 6 to the 5/2. 6 to the 2/3, that's 4. Plug back in, 3/2, and c. So we are all done with that one. So we're going to start in the same spot by finding the composite function, which is the denominator, and finding the u, which is the inside function of the denominator, and finding the du, which is the derivative of that with respect to x. So of course, we'll put a 1/2 out front so that we have that full du. But that leaves us with an x squared minus 1 on top. So what we could do first is separate it into two functions. Square root of u, du we have. And we're going to be subtracting the integral of 1 du over the square root of u. So this second integral is coming from just this -1 right here. And this is taken care of. We could just do a power rule. But this left side, we're going to have to do that change of variables. So let's take this u. We don't know what x squared is, but if we can figure out what x is, we could square that to figure out what it is. So let's see. Let's add 1 and divide by 2. So u plus 1 divided by 2 is equal to x. So x squared is just that squared. So 1/4 u plus 1 squared. So I'm going to distribute this 1/2 to each of these integrals. That way we can focus on them separately. So 1/2 times the integral. Let's see, x squared is going to be that 1/4 thing. So let's also take out the 1/4. That's going to leave us with u plus 1 squared over the square root of u on the top. And the second one, when you distribute the 1/2, it's going to be -1/2 du over the square root of u. So again, the right side we can focus on later. For now, let's get rid of this ugly left side. So what we're going to do is FOIL out that numerator and then separate it into 3 different fractions. So let's see. It's going to simplify to a 1/8 out front. If we FOIL it out, we're going to get u squared plus 2u plus 1 all over the square root of u. Now, let's separate that into 3 different fractions. So when you're dividing, you subtract exponents, right? So it's actually going to become the integral of u to the 3/2 plus 2u to the 1/2 if you subtract the exponents, plus u to the -1/2. And we're going to subtract off -1/2 of the integral of u to the -1/2. So, let's see. That's going to leave us with 1/8 times 2/5 u to the 5/2 plus 2 times 3/2 u to the 3/2. I'm sorry, 2/3. And 2u to the 1/2 if you do all those power rules. And then you're going to get minus 1/2 times 2u to the 1/2 when you do that power rule. 2 cancels with 2. And let's see. Let's also distribute this 1/8 in and plug back in the function for u. It's a tough problem, but 1/20th, u was x, 2x minus 1. Right, yeah. To the 5/2. And then 4/3 is going to give us 1/6 u, which was 2x minus 1 to the 3/2 and 1/4 u to the 1/2 minus u to the 1/2. So, of course, that's followed by a plus c. Let's just simplify out these last two and also plug back in the function of u. 1/20th, 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2. 1/4 minus 1 is negative 3/4. Plug back in the function of u, 2x minus 1 to the 1/2 power plus c. That is the final answer. And now we're going to move on to the last example set. Let's do some definite integration. So the trick with this is that these bounds are a function, or are bounds of x, and this is a function of x, and this is integrated with respect to x. So we have to make sure that, like, if we have a function of u and du, that our bounds are not still in the x, and vice versa. We don't want our bounds to be x and our function to be of x, but not with respect to x. So let's see, let's just do what we normally would do, a substitution for the inside of the composite function, and the derivative, du, which is 2x dx. That works out because we have the x dx, so we can put in a 2, account for it with 1/2 out front. So boom, this turns into the integral 1/2 times the integral of negative 1 to 1. We have our du now, and we have our u cubed. So ignore the bounds. Let's just focus on the indefinite integral. It's 1/2 negative 1 to 1, or I should say, let's just focus on the indefinite integral. So add 1 to the exponent and divide by that new number. There's not going to be a constant, and we're going to evaluate this. Well, first, before we evaluate it at the bounds, let's put it back into our function of x. Because the bounds, if we just put in our 1 and our negative 1 into the u, we can't do that because those are bounds of x. So let's just plug back in our function of u, which is x squared plus 1, raise it to the 4th power, and now evaluate it at 1 and negative 1. So using the second fundamental theorem of calculus, remember, we're going to take that x squared plus 1 to the 4th power and evaluate it at b, which is 1 squared plus 1 to the 4th power minus f of a, which is negative 1 squared plus 1 to the 4th power that leaves us with 2 to the 4th power minus 2 to the 4th power. So we're just going to get 0 as our final answer. This is because the graph must be symmetrical about the x-axis, so all of this negative area from -1 cancels with the positive area of +1. And anyways, moving on to this question, 0 to 4. We're going to start with the substitution again, which usually, once you get out of the beginning of calculus 2, all integrals will have to deal with some type of substitution. U is equal to 2x plus 1, meaning that du is going to be equal to 2 with respect to x. So we want that 2 in there. Let's put a 1/2 out front. Now we have our du. So let's rewrite this as the integral of 1/2 1 over the square root of u du. This is just an easy power rule, and we did it a few times already. 2u to the 1/2. 2 cancel with the 1/2, and we should evaluate this at 4 and 0. But before we do that, we have to plug back in our u. So it's equal to 2x plus 1 to the 1/2 power, evaluated at 4 and 0. So let's plug in 4. We're going to get 9 to the 1/2. Subtract off 1 to the 1/2. 9 to the 1/2 is 3, and 1 to the 1/2 is 1. So it's 3 minus 1, or just 2. And that is it for our definite integration and practice problems involving integration by substitution. Hope it helped.